Our distinguished guest today is Professor J Solomonoff, who came up with the concept of algorithmic complexity in 1960, which was about 5 years before Kolmogorov and Shahidin came up with a roughly similar idea. Especially, not only describing a concept for the first time, but also using it in a particular way. While Kolmogorov and Shahidin ended up studying complexity and computability, Professor Solomonoff put together a universal theory of inductive inference and proved that it's a valid one. So we have the great honor of having him here today, giving us a lecture on algorithmic probability, artificial intelligence, and NKS. I would like you to please join me in welcoming Professor J Solomonoff.
Since, I guess the time of Laplace, the universe had been thought of as a huge computer, an analog computer, however. You just feed in the initial conditions and it sort of cranks itself out and goes on, and that's it. So since then, physics has pretty much followed along in that model. Since then, however, in trying to simulate a lot of the part of the universe, they've used mainly digital computers. And people began to think that, well, maybe there are some good digital models of the universe where you don't have to go through this analog conceptions and you go use digital models directly. And there had been a lot of thought about this, but no great groundswell in the academic community, to put it mildly. So what Wolfram has done is he's put together a lot of these ideas in this area to try to get people interested in it. And he's been, on the whole, pretty successful in this, and there is a lot of interest now. Infinitely more than there was before he started talking about it. Anyway, that's what NKS is. Now, the relevance of what I'm doing is this. My theory of inductive inference, how you do science and things like that, has to do as a purely digital device. You can you get analog data into it, but you have to convert it over using some sort of analog to digital conversion, and this is a very subjective thing. But anyway, if you have digital data or digital model, this will feed directly into the theory, and it'll tell you how good the thing is, and it will enable you to compare it to other theories, so you know whether you're doing anything. Furthermore, it'll give you a relative goodness. How good is your theory relative to some others? It won't accept or reject anything. In fact, I don't think any good inductive inference device should ever accept or reject something. Whenever you accept or reject something, you're throwing away data, and this is something in science that you don't do unless you absolutely have to. When you make a final decision, you throw away data, but only at that point should you do this. Now, getting back to just what algorithmic probability is and some criticisms of it and some, some properties of it, and replies to the criticism. First of all, the way it works is this. Supposing we have some data that's in the form of a string of symbols, zeros and ones, say you have a long string, we'll call it X. And you want to get the probability of the next symbol in terms of the previous ones that have gone before. This is a general problem in science, and just about all of the problems in science can be taken down, put down into this form. It's a problem of prediction. Much of science appears to be in the form of making up theories, and a lot of scientists think that making up theories is what science is about. I don't. In fact, the algorithm of probability in theory doesn't use theories at all. It goes directly from the data itself in digital form to make predictions. And there are elements in it that can be associated with theories, but they're not necessary. It's a purely formal method of going from data to predictions without any necessary intermediate forms. Now, so how does the thing work? Well, first of all, we start out with a universal device. I used universal Turing machines because a lot is known about them, and it's easy to form them so that this theory fits into them. However, any other kind of universal device will do, but you have to make allowances and somehow changes in the theorems to allow for them. Anyway, the idea is this. If you have some sort of a universal device with an input and output, to get the probability of a particular string, what you do is you feed random input, purely random bits into this machine, and it will have some kind of output. The probability that that machine will give this particular string is what I call the algorithmic probability of that string. Now, how do we figure this? I don't know how visible that is. Well, anyway, what this means is the probability of the string X with respect to machine M is this. You take any particular string, input string to the machine that could conceivably produce X followed by some other bits. And the ith program of that sort will have a certain length. Now, the probability of that particular program being produced as random input will be 2 to the minus length. Say it's 10 bits long, it'll be about 1 chance in 1,000, 1 chance, 1,024. So you take all the different possible ways that this X could be created, and you add up their probabilities, and that's the probability of X. And that's all there is to it. Now, this is a fairly simple definition, and you think, well, why all the argument and difficulty surrounding it? Well, there are a couple of difficulties here. The first one you come up with is that usually you can't compute this. And the reason you can't compute it is this. There are some inputs to this machine. You put the input in and you want to see, is it going to produce X? Well, it produces the first, say, 3 or 4 bits of X. And then you wait a while and see what's going to print next. You wait a while, it prints the next bit. So you wait some more and see for the third bit. Well, you wait a long time, it doesn't print anything, but it keeps calculating. Well, it turns out that there's no way to find out whether it ever will eventually print it or not. So for that reason, this is incomputable. But it is computable in one sense. You'd always make an approximation and you say, well, I'll use this time t as a maximum for any of these tests. So that makes the thing computable. This is not a particular efficient way of doing this. There's a much better way I'll show you to do the approximation. What it does is, this formal definition is, however, extremely useful in this sense. You can think of these individual programs as being individual theories. And what it does essentially is it takes all possible theories that you might make for assigning probabilities to X, and it assigns a weight to each one depending on its length, or in this case, how many bits it takes to describe the theory. So this is a good way of integrating all the different ways that we have of doing inductive inference. Now, an approximation to this is this, which is called minimum description length or minimum message length. And what that does is you spend as much time as you want to looking for a theory or a model for the data. A model is something that enables you to, given any string, to the model will give a probability for the next, thank you. The model will give you a probability for 1 being the next bit of the string. So given a model of that sort, you could assign a probability to any conceivable string, okay? Now, minimum description length is this. It says it looks for a model such that, looks for a model so that well, let's see. Of X with respect to mu what this means is that the value that this number here is equal to, this is the probability that the model mu assigns to the string X. And this is the probability that we assigned to the model mu, and it's something like the description length of it. How many bits do we need to describe the model? So we multiply the, you might say, you multiply this times the probability of X as given to the model, and you want to find a theory or a model for which this probability is maximized, okay? Now, in algorithmic probability, you just simply take all possible models and you weight them in this way, and the one with the shortest description, of course, gets the most weight. Now, in general, you can't find the one with the shortest description, and you use the best one that you find in the available time. Now, this particular definition is pretty good, as I'll show you later. There's a theorem that tells how accurate the thing is. And so the question is, why would you use such an elaborate thing when you could use other computable probability measures that people will give you that more or less work? Well, the fact of the matter is that if you use any computable probability measure this will be equivalent to using only some of the terms of this sum. And it means that you're leaving out some other ones, because you can't know, you certainly won't be including the incomputable ones, but there will always be other terms that you will not be including. And for this reason, there are regularities in the environment that these systems will, of necessity, be blind to. So by using the value of probabilities that's the highest value that you could find in the available time, this is sort of the best way you could be spending your time looking for models, and it'll give you the best possible probability that you can in the available time. Now, I've been telling you how that this is a great probability model, and when I first discovered the thing in around 1960, I felt it was pretty good, and it seemed to satisfy a lot of reasonable assumptions about it. For one thing, it seemed to be something like Occam's razor that gives a lot of weight to things that are simple. It also went along with the idea that of coding theory, that when you did compression of data, the amount of compression that you get is proportional, depends on the probability that you can assign to the data using some sort of system. So however, I wasn't really sure that the thing was correct. Around 8 years later, around 1968, I finally discovered a way to really measure how good this thing was, and it turned out to be very good. Here's how good it is. Now, this assumes that you have some data that was generated by some stochastic source, which you'll call mu. Mu is some sort of equation that allows you to associate probabilities with any particular string, and it could give you the probability of the next bit given the previous ones. And P sub m is the same sort of thing that you get from algorithmic probability, okay? So you wonder if you have this string and you're given probabilities, predictions for the next bit being 1 for P sub m, and you also get it for the distribution that actually generated the string. So you wonder how different are they going to be? And this is the difference between the two, and you square this. And then you add up all these squares for the length of the string that you have. And it turns out that the expected value, expected being with respect to this generator, the expected value is going to be less than a certain constant. Now what this means is that no matter how long the string is, this total error is going to be bounded. And this is a pretty strong result. Furthermore, if you look at this thing that it's bounded by something, it's bounded by the logarithm of the probability of mu as described by m. So if m, the reference machine, has instructions that make it easy to describe mu, then this is going to be very small. On the other hand, if mu is very distant, it's something that you wouldn't think of, and your machine doesn't have take very long instructions for it to describe it, it will always be able to describe it because it's universal. But this error will be large. It will eventually, if you get enough data, if n is large enough, the individual errors on the individual bits will get down to very small ones because the total has to be bounded. So no matter what you do, I think that the error that this thing gets is smaller than any kind of statistical device that you have, and it's more general. Now, this particular version of the theorem is for when you have finite descriptions, when this is a finite number here. There are also versions where you have infinite descriptions, namely the model you have will have several continuous parameters, and in which case a continuous parameter can have an infinite amount of information in it. But for a finite string, you don't really need that, and you can sort of cut the thing off. So because of the strength of this theorem, it becomes worthwhile to deal with the difficulties inherent in this particular model. And my impression is the difficulties in the model aren't any more difficult than the difficulties you run into in inductive inference in general. Because whatever kind of model you use, as I mentioned, if it's a finite model, that is, if it's computable, then you know that there's something wrong with it, and there's no way to avoid it. So this just tells you to spend your time, as much time as you have available, looking for better models, and it tells you which model is better than which. So you can't do any better than this, as far as I can tell. It really tells you the induction problem is a time-limited optimization problem. It's not a question of getting the exact right probability. It's just a question of getting as good a probability as you can get in the available time, and there's no way to avoid it. And this just tells you how to do it. Now, this particular model is based on universal machines, specifically Turing machines, or it could be any other kind of universal machine. And as I pointed out, it's the universality of the thing that seems to give the trouble here. So I want to take a look at exactly how this arises and how we might try to get around it, and what happens when we try to get around it. In recursive function theory that deals with things like Turing machines, one way to categorize functions is of three types. The first type is the easiest type. You have a bunch of functions like sine wave or squashing functions in neural nets. And you have addition and subtraction and multiplication. And you could use these operations, you can compose these operations, these functions, to get larger, more complex functions. For instance, you could take 3 times sine of 5, or 3 times the sine of and so on. Here what you're doing is you're composing functions in this manner. And there you could get arbitrarily complex functions in this sort, and you get a certain kind of universality in this way. For instance, using only sine waves, it's possible by using functions of this sort, just addition and multiplication and sine and cosine, to get the approximation of an arbitrary function to a continuous function to arbitrary closeness. Another thing you use is you could use powers of x, also do the same sort of thing, get infinitely close approximations. And another thing that is used in neural nets is use a squashing function like this. And also there you will get a kind of universality in that these are able to approximate with arbitrarily closeness. The function used in neural nets is a little bit different from the kinds used in Fourier analysis and used in Taylor expansion, however. And it's able, to some extent, to do this somewhat more economically. As a result, it's somewhat better for prediction than other kinds of things, I think. There was a paper a few years ago explaining how this works. In order to do an approximation of functions using sine waves or power series, just linear combinations, the number of functions you needed increases at a certain rate, depending on how much accuracy you need and how much the function that you want to approximate wiggles around. And the number of points you need using functions like this are smaller, significantly smaller. And the way it comes about is that if you have a function like that, it looks like this. In neural nets, you're able to adjust these functions in 2 ways. You could squish them this way, and you could also squish them this way. And then you add them together to get the, you convolute, you compose them to get the desired waveforms. And this is much more general kind of operation than the thing of simply taking sums of power series or sums of trigonometric functions. It's much better and very significantly better. Now, the theorem said that you need fewer points fewer coefficients or to get the desired accuracy. The paper didn't say how much precision you needed. It may turn out that it's an illusory gain because the total information may be the same in each. I wasn't able to figure out how much accuracy was needed in this, so I can't really report to you whether this technique is actually better. Empirically, neural nets does seem to be better than linear prediction. In a prediction contest in 1992, some people at Santa Fe Institute made some large data sets in various areas. There were 6 data sets, and you just download on the net bunches of data, and you're supposed to use it for prediction. And they compared different methods that people use for prediction. The methods they used were mainly linear methods and neural nets and space state reconstruction, which is a method used in chaos theory to make chaotic models. In all 3 of the techniques, 3 of the problems that they were able to make comparisons, neural nets came out better, except in one where they used a combination of neural nets and state space reconstruction. So neural nets at that time was pretty good. Since then, a lot of new techniques for prediction have been investigated in the machine learning community, and I don't know whether, I sort of doubt whether neural nets is still way ahead. I'll get back to this a little later, though. Okay, I described this first part, the first order of complexity of functions, where you have a composition of a bunch of different kinds of functions. The second order of complexity is what are called primitive recursive functions. And they include this, but they also include one extra instruction. Or some other, anyway, it includes this single extra kind of instruction. It's the for loop. It has it's for I equal 1 to n, where n has to be specified in the loop. And this gets you an enormous increase in the kinds of functions that you could do. Now, that you could do economically. Superficially, what it does is this. Supposing that n is 83. You could get the same function in this area here, but it would be 83 times as big. It would take you 83 times as much information to describe it. So it would get tremendous, enormously less weight in here than formulas in here. So what this does is it enables you to functions that would be simply impossible because they have too long a description become possible when you have this simple loop here. And one of the things that you can do that I believe neural nets are not able to do if you have functions of this sort are this. For instance, if you're using this kind of thing, it's possible for you to give the machine examples of in which a sine wave would be a good fit of a function. Then later, you give it some more examples, and a sine wave is again useful, but it has a different phase, it has a different amplitude, and it has a different frequency. But this thing can recognize that it is a sine wave, and just change the parameters slightly and fit the thing, and look upon the new and the old sine wave as just part of a extended data sequence. These guys can't do that. And it's a tremendous increase in power that you're getting there. There are other things that this could do. One of the inputs is n. N has to be an integer in this case. And that gives another additional degree of flexibility, but I can't tell you exactly, give you a good example of it. Now, the third level, now, up to this point, all these functions are computable. In all cases, since n is finite, you can make even guesses as to how long these computations would take. And in all cases, they're always possible. And so up to this point, there's no problem of incomputability. As it turns out, these functions can take you so long to compute, however, that they could be effectively incomputable. So if you have 10 minutes to do your computation, you're going to run into incomputability anyway, even though theoretically these things are all computable. Now in the third case, we have an additional kind of thing. This is another kind of loop. Let's see. Oh yeah. Do and then there's some equation here, and then loop. So this is the same as this thing, except that you don't have to specify the n. You have some kind of criteria here that may or may not be numerical. It could be very rough. And it says just do this thing again and again until the criterion is satisfied. Now, it may turn out that this criterion is never satisfied, and you can't know in advance. So, and you can show that there are functions in which it's actually impossible to tell ever whether this thing will ever converge or not. So this is these are called partial recursive functions, because in some cases, if you put in values, the function will have a value and sometimes it won't. And sometimes you could tell which ones they are, and sometimes you can't. And the ones where you can't are the ones that give trouble. So this gives you an additional expansion to the kinds of functions that you could use. Now, I don't know how much extra it gives you. In the recursive function community, when primitive recursive functions were discovered, and it was thought that possibly, well, no one found any functions that were used in science or anywhere else, for that matter, that were not primitive recursive functions. And it took a long time before the Ackermann function was found. And the Ackermann function is a partial recursive function that increases so rapidly that it couldn't be a primitive recursive function. Now, the funny thing about the Ackermann function is that, as far as I could see, it is representable in a way that in which you ought to be able to express it as do loops of this sort. So I don't know exactly why that's true. So I intend to investigate this in greater detail to find out exactly what it is about the Ackermann function that makes it not a primitive recursive function. But since the Ackermann function is, the functions in this area are extremely rare, it may turn out that primitive recursive functions are okay, and you could forget about, for practical purposes, you could forget about the incomputability of this. But as far as practical is concerned, you deal with it in exactly the same way as if it were incomputable. You have to use something like this, Levin's search procedure, which I will describe, to avoid excessively long descriptions or computation times. Now, the way you the way you deal with this long description time thing is this. So you're hunting for codes that might be appropriate for S. So what you do is you pick some small time, say the time of 10 instructions on your machine. If it takes 1 nanosecond for an instruction, you start out with t equals 10 nanoseconds. Okay, then you try all instructions such that, say this is a sequence of possible instructions that you want to try, and S sub I is the sequence, and this is the length in bits of the sequence. So this is how much time you spend on that one. Now, the thing about this is CC by I is your computation cost. So you want your threshold for how much time you'll spend on this depends on you multiply by t, and if it's a very long program, you'll spend very little time on it. A short program, you'll spend plenty of time. So you examine all of the programs that satisfy this, and this will only take you a finite amount of time, because if you add up all of these times, it's going to be less than t times and this thing here is always less than 1. There's a theorem to that effect. So the time it'll take is less than t. So if you don't find anything useful at that time, you double t, and you go through the whole thing again. If you don't find anything, then you double t, and you keep on doubling t until you find what you want. You could show that the total time that you need to hunt for something is going to be something like this. This is the time it takes you to test the jth string, and this is the length of the jth string. So it's t sub j times 2 to the L sub j. This is the total amount of time it'll take you to find this. And it's in absence of any other information, it's the best time you could do. And looking at this, you think, well, isn't this pretty bad? I mean, here you have this exponential thing here. Isn't that going to take a lot of time? Well, it would ordinarily, but we sort of cheat. And the way we cheat is this. We arrange so that L is quite small. And the way we do it is this. We start out with giving a machine, say, simple problems in a sequence. And after it solves the simple problems, it will modify its vocabulary so that those problems could be solved more easily. They'll make up definitions and things like that. And what this does is it reduces the length of programs needed for more complicated problems. So while this looks like an exponentially difficult problem, and it is, the way you deal with it is that you make L small. And that's the only way you could solve it. Ordinarily, if you just use the ordinary program length, it'll be too long and you'll never finish. I will discuss this in more length later now. Oops, not here. Are there any questions so far?
Yeah. The question in the discussion you just had, I missed what it is exactly that you were going, or what you were trying to find. I mean, what is the? I didn't know the problem that you.
Okay, the problem I'm trying to solve is normally you're looking for short codes for this, okay, and well, I think I transitioned to another problem, but. Yeah, in this thing you're looking for short code, and you do this, which is sort of something like Levin's search procedure, to decide how long you want to spend looking for each one, because some of them will take an infinite amount of time.
I'm not sure what the input is to the problem. I still don't know what the input is to the problem, what the problem is actually. I'm sorry. Is the input a string or
yeah, the input here is a string X.
And so then
You're looking for codes for X.
And M is fixed in this. I mean, M is some machine that is fixed. I mean, the SIs describe various types of machines, right? I mean, there are sequences of instructions.
The S is a possible input to the machine. The machine is fixed, okay? And S is a string that is an input to the machine, and you hope that it's going to come out with X as a code, okay? So now all of the inputs that you have in general, most of them won't give you X, see? But but to find out whether they give you X or not is going to take a certain amount of time, and some of them may take too long. So this tells you how to limit that. Okay. Yes?
On your third thing there, do until, you mentioning a link to the Ackermann's function. So I'm remembering the 88's Harris-Harrington theorem, where you go to things that are worse than Ackermann, like Don Knuth's arrow notation.
Oh, you mean they're worse than Ackermann? Yeah. Uh-huh.
And then you get basically Gödelian situations in actually simply statable problems.
Mm-hmm.
Is that, can you push that further back and say that that's a default of do until, or is there a further kind of condition?
As far as I know, this is this is the end of the line.
So
That is, these functions here, a full universal Turing machine will, this is all it does. Now, you mentioned some other things that are even worse than Ackermann. I didn't know about this.
There was a wonderful column Martin Gardner did in Scientific American a while ago,
Uh-huh.
which he was talking about these connected dot games and Ramsey graph theory.
Yeah.
The problem with Ramsey graphs is there's no symmetry.
Yeah.
It's connected to everything, as close as
Yeah,
it can be.
yeah.
And in trying to compute some very simple coloring
Mhm.
problems, I mean, there was a specific problem was connecting the dots on a hypercube
Uh-huh.
or an n cube.
Mhm.
The problem was how many dimensions did the cube have, and being forced to commit to making a plane, like finishing off a square.
Mhm.
So that basically, you can look at the points of a hypercube. In this case, the answer was 6. Everyone was certain it was like an I Ching space, 6
Mhm.
points. But to prove the existence of a finite solution, Ron Graham had to generate this thing with arrow notations for utterly unbelievably huge numbers and ridiculously fast. And it was the largest number ever used in a serious proof
Mhm.
to prove something was actually equal to 6.
So it was something like Ackerman of 6 or something
Way
like
beyond.
way beyond.
I'm trying to remember how it worked, but it's like towers of exponents.
Mm-hmm.
And if you have three,
Sure, yeah.
It's 3 to an arrow and 3 to the.
Sure. I know, yeah.
And his thing was stacks of 64 deep.
Yeah.
With arrows in the arrow.
But in general, these, as far as I know, we don't use these very often. And it may be that they come in some hidden way. I don't know. But so far, they don't seem to be terribly useful. But as I said, it doesn't make much difference. If you have this Turing machine, cutting out these rather than not doing these won't save you much time, I believe. Though, I don't know, it may turn out that you can somehow. Because in the case of these, you could tell whether the things converge or not, and you could devise Turing machine programs in which this never occurs, in which this uncertainty never occurs, and you avoid those kind, I believe. How much loss you get in expression possibility is something I have no idea. The next part, I'm going to talk a little bit about some developments in machine learning and how I'm going to use them in this stuff. Since 1992, when they had this contest that I told you about, there have been a lot of developments in machine learning, and there's some of the more effective, popular techniques are these thing called support vector machines, Boolean belief nets, genetic algorithms or genetic programming, which are similar and different. Also, recurrent artificial neural nets, which are considerably different from the normal feed-forward neural nets, which is what I've been talking about. And then, last but not least, PPM, which is prediction by partial match. Well, it isn't last either. That's also another one is grammar discovery. Now, support vector machines and Boolean belief nets are in the area of here. They're non-recursive methods, but they could be very good. Genetic algorithms and genetic programming can use an arbitrary language for optimizing, so they could be Turing machine universal. Recurrent neural nets are the same as ordinary neural nets, but they have connections that go backward. An ordinary neural net would be like and this would be a simple, about the simplest possible neural net that you could have. That's a feed-forward neural net. Now, a recurrent one could have some of its outputs go back to the input, like that. And this change makes possible an entirely different kind of game. It makes the thing full Turing universal possible, and also very difficult to figure out how to train them. One of the great breakthroughs in feed-forward neural nets was the fact that there was a simple rule by which you could train them on the basis of any arbitrary data. It took a long time, but it worked. Well, with recurrent neural nets, there are training algorithms, but they take enormously longer and much less efficient. Now, that was theirs. Now, the other part was grammatical discovery. This is something that I was interested in early 1960s, and I wrote a criterion for the discovery of grammars to fit some data. So supposing you had a bunch of text in some language, and you want to find a grammar that's appropriate for it. So I devised a criterion using this for deciding what a good grammar was, or how to make predictions using grammar, and I was pretty enthusiastic about it because this was an entirely new way of doing prediction from anything that had been done in statistics before that time. Well, I figured that, well, I got this criterion for discovering them, and I didn't do any more work on it. I just sort of published it, and I figured that mathematicians would work on it because it was a well-defined problem. Well, they did a little bit, but it turns out it was a hard problem, so they didn't make much progress. However, recently, since about 1990, 1995, there has been a lot of progress in that, and they've gotten techniques that do discover grammars fairly well, and this is an essentially different way of extrapolating data from anything that has been done before that time. So I was much interested in it, and I do have ways of using it. PPM is another variant. It's something that is very simple, and it's relatively accurate and extremely cheap. In other words, it takes relatively little memory and little time to implement, and yet it's pretty accurate. What it does is this. It's a prediction, it's a compression algorithm. The earliest compression algorithms were Limpo-Ziv, and they start out with 8 bits per character, and by using Limpo-Ziv, they compress it down to about 4. This is Limpo-Ziv is the commonest zip algorithm used for compression. Now they have a thing called BZip2, and this compresses down to something like 2.6 or so. It's a factor, this is a factor 2, this gives a factor of 3 about. And there were variants of this, improvements. In fact, there was a sort of a subgroup in the compression community that had a kind of contest for how much compression they could get out of this. And they've gotten down to about 2 to maybe 1.7 or 8 or something like that, bits per character. Now, way down here are human beings. The best human being has gotten 1.3. Now, the way these are computed is this. All of these compression schemes can be looked on as ways to predict, give a probability distribution for the next symbol given the previous ones. And the way this worked is they would just give a text to some people and say, well, I want a probability distribution for the next symbol, okay? And they're allowed to read any part of the book up to this point. Then they tell them what the symbol is, and they ask for the next one, and so on. And you get, I think they had maybe about on the order of 100 symbols to predict. So there were, this is the goal, and some people in this group feel that they could achieve this goal without any great trouble, but I don't know whether, the last I read was a few years ago, and I don't know how much progress there has been since then. But the point is that this method here is relatively cheap, and I found a very nice way to use it to accelerate finding of solutions to these problems. And the way it works is this. This is PPM, by the way, all of this stuff here. Prediction by partial matching. The way it works is this. To do prediction of English texts, one easy way would be to look at the previous 3 letters and then look at the complete corpus to see the probability distribution of letters that have followed these 3 characters. And the longer a string of characters you use, the better prediction you get. However, you can't use very long because if you use like 10 characters, most cases of 10 characters will not have occurred before. So what they do is this. They take the text, of letters, and they want to predict this one here, okay? So what they do is they start out with what is the longest sequence that we have here that has occurred before. And this is essentially what Lempel-Ziv does. Anyway, at that point. But here it begins to depart significantly from Lempel-Ziv. What happens is that will enable them to predict one symbol, the one that had occurred, say, once before. If this sequence has occurred once before in the set, or if it always had the same prediction. So that will be the most likely one. However, say that letter is A, okay. Now, they want to see what what the probability of B is, so they look back and they see what is the longest string in the past that that ended with a B that was like this, and it may be much shorter. So in this way, you get different strings for different predictions, and you have different amounts of data for them. And PPM is a way of weighting these different predictions and getting reasonable probability models for values for all the different possible predictions. They also, one of the most important problems is what do you do when the letter occurring here has never occurred before? And this is an important question that they devote a lot of time to and get some reasonable answers to. Okay, now I don't want to go into this in any greater detail because I don't think it's terribly relevant. I just want to give you some idea as to how the thing works. Now, now note that the function here is you're given it a sequence of symbols and it gives you a probability distribution for the next one, okay? That's what it does. Now, any of these other things can do the same thing, and they have different computing costs to do them, and they have different degrees of generality. The most general ones are these here, genetic algorithms and recurrent neural nets, but they're also the most expensive. And there's a trade-off between the precision that you get in prediction and accuracy, and we have this here also. If we don't have much time, we're not going to get very good predictions. And there's no way around it. I worked out a way, though, in some of these methods, there's an actual trade-off so that you know you can spend as much time on these things as you want, and you'll get more and more precision. And I worked out a way to decide in practical problems just what is the optimum amount of time to spend so that you end up with the best performance per unit time. But we won't need that at this point. The way I'm using it is this. I mentioned in Levin's search procedure that you had this problem of exponential search time, and the way you solved it was you arranged so that the exponent was small, which seems like cheating. Well, here's how you go about doing this cheating in more detail. The problem I was really interested in is not exactly sequence prediction, but the problem of AI. The problem is here that I was interested in is this. You have a entity, this machine, and you want to get it to be very smart. And the way you do this is you give it easy problems to solve. And it has a simple algorithm for searching for solutions to problems, and it solves the first ones very easily because they happen to have very simple solutions. Okay, now having this set of solutions, it has maybe 10 of them. These solutions were found using Levin's search procedure. It looked for shortest ones first and so on. After you get these 10 solutions, what you do is you use one of these techniques to form a probability distribution on trials for you. So you use the first 10 examples as being sort of good examples, and you want to extrapolate that set probabilistically. And you use any of these devices, I would use PPM, say, to generate trials in order of probability, and you use them with L-search to find good answers. And the better distribution you get from this, the shorter your search is going to be, and the more effective compression you get in the final solution that you get. And this is essentially what I plan to do. I plan to take advantage of the real goodness of these modern machine learning programs to help in Levin's search procedures to find solutions to problems using universal devices. The solutions will use a complete universal set of all three kinds of functions, and yet they will use these simpler search techniques that are not necessarily universal to help find them. So that's the trick. I haven't tried it out yet, and I look forward to it being successful. Now, this general thing that I've been described, I personally haven't programmed it. A colleague of mine has programmed something like it that he calls OOPS, which is optimum, let's see. Well, it's some sort of optimum ordered problem solver. And what it does is, instead of using a universal Turing machine, it uses a language that is sort of equivalent to one. The language is called Forth, F-O-R-T-H. And it's an interesting language in several ways. First of all, it's about the simplest language that you could think of. It has a stack, and it puts instructions on it, and that's about all there is to it. Though it's Turing universal, you could write a interpreter for fourth and a few thousand bytes, and the programs it writes can be made about as fast as a fast machine code. They're extremely simple, and it's a very good language. The guy implementing this was named Jürgen Schmidhuber. He's in Switzerland, and he didn't really take advantage of all the features of forth, so his take much longer. He uses about 1,000 machine instructions to get one fourth instruction, which is, I think he just wanted to see whether the thing worked, and he didn't want to necessarily optimize it. But his program did do something that was quite spectacular. Using a small training sequence, he was able to get it to solve the Tower of Hanoi in a recursive way. So it had a general solution for arbitrary size, and I don't think this has ever been done. It took a pretty long search to do this, and the search was about 1,000 times faster than it would have been if he hadn't used a training sequence. I've been very critical of this because I feel that he could have done it better, but it does illustrate the utility of the general system, I think. And the work I will be doing will be something like what Schmidhuber has been doing, but it'll a lot different also.
So did you find an actual program that on any given, for any given n, the Hanoi problem solves it? Or did he just find one that would do it for, n below, say, 100?
No, it'll do it for, it's general, it's general, yeah. It's a very simple recursive function. Yeah. And that was sort of a breakthrough. The way the thing works is this. The previous part of its training sequence contained a program that had a recursive solution, but the program was very, very simple. It was nothing like the Tower of Hanoi. But it used instructions that were useful for recursion. So in his program, he has a operation called boost. And boost does this. Boost 3, with 3 as argument, means it takes the third program that has been successfully completed, and it looks at the frequency of instructions in it. And it uses that frequency to modify the frequency of instructions to be tried in the new program. So it takes the frequency in that old one, and it also adds to it some, so that a lot of other instructions are also legal, but less probability, that's all. And with this trick, he was able to multiply by 1,000 the effective speed of the, or it took 1,000 as long to do it. I was complaining about it because the figure of 1,000 is due to the fact that he started out with too many instructions. He started out with 73, and he really didn't need that many. Also, there are other ways of getting a similar effect, but I think the boost instruction was a really neat trick, and I haven't figured out. Well, it needs work. One of the complaints is that it worked because there were very few programs to start out with, but if you've worked 100 problems so far, boost can have any argument from 1 to 100, and the chances of your hitting one that'll help you rather than hinder you aren't so good. So there are ways of dealing with this, and I think this can be fixed. Do you have any other questions? Yes.
This is going back a bit, we were talking about grammar discovery.
Yeah.
I'm in a new business venture with 3 other people. One
Okay.
of whom you may know, his name I don't know, Quinn Tyler Jackson.
No.
His PhD was this year, and he's like mentored by Bjorn Strustrop of C++ and all this. What he's got is it sounds like what you're describing. I mean, it's an incredible parsing engine. It's pretty universal. And I just happen to have this PhD with me because I have to read all this. I'm trying to put the stuff I was talking about earlier together with what he's doing. They've already got some contracts. I have to like get up to speed on his thing. So I brought it with me in case I had some downtime.
There's been a lot of work in language analysis, for instance. Some spectacular results in machine translation, for instance. You may have heard about this, where they just take a parallel text from arbitrary languages, like you want to translate from English into Chinese or something like that. And you give it English stuff and you give it the Chinese text that's parallel to it. And it looks at a lot of this stuff and it figures out pretty good translation rules. Better than most of the ones that have been designed by really arduous creative work, actually. It's a pure computer program with no input other than these parallel texts.
It sounds very similar to some of the things Quinn is doing, although I can't say definitively until I read stuff. He's telling me things.
But there have been several groups working on stuff like that with great success, and I haven't figured out how. I haven't looked at it closely enough to know whether I could figure out how to use it. Because some of this stuff I'm doing is close to machine translation in the sense that you have one thing and you have an answer to it. And one of the kinds of problems that I'm starting out with is a question-answer machine that runs something like this. You give it a bunch of question-answer pairs. Now, you could think of these question-answer pairs as being in English, or they could be the input and the output of some unknown machine. They could be numerical, they could be symbolic, or mixtures of those things. There are an enormous number of problems that can be put in the form of extrapolating this. Then, given all these, you're given a new Q's up to Q sub n, you're given Qn plus 1, and you want to get a probability distribution on this here. So this is a very nice general problem, and it's easy to put data into it because there are a lot of, one of the things I wanted to start out on was algebra. I want to teach the thing algebra, just elementary algebra, and the way I was going to do this is to start out with algebraic notation, and then I wanted to learn various definitions. Definitions of things that you normally have in programs like Mathematica or Maple. These are, for instance, one of them would be like integrate, or any of those things. And those instructions are very, very useful things. Much of our knowledge in science is in the form of definitions. And you might think of the progress of science as being mainly defining new things. But anyway, so I was thinking of doing that, and it's a sort of easy way to get training sequences. And for some of them, extrapolating them can be arbitrarily difficult. Like, for instance, supposing you've taught it what integration means. So You give it very simple problems to integrate. Well, they could become arbitrarily difficult. And you can give it training sequences of simpler and simpler integration problems, or ones that use certain kinds of techniques that you want it to learn. So you give a lot of those. So the way I looked at this is that ultimately designing a training sequence for this device would be the hardest part of the whole thing, and that the formal methods that I've described here would be ultimately the easiest part. Whether this turns out to be true, I don't know.
I have a problem.
Yes?
That is related to this.
Yes.
I work in the area of databases, and we often face this following situation. We
Yes.
have a particular input and we have a possible output.
Yes.
And in the simplest form, this problem is we're working in a specific language. I mean, it's a formal language, say,
Mm-hmm.
first order logic or something like that.
Yeah.
You have two relations, a graph here and a graph there.
Yeah.
And you ask yourself, is there in fact a first order statement that takes this particular instance relation into that one?
Mm-hmm.
Now, in general, it may be or may not be. I mean, there are cases where, you know, the answer is yes, there exists one, and cases where there doesn't exist one.
Yeah, well, you
So
do a
the
search.
issue that I have here is what I don't understand is when you talk about question answers.
Yes.
It almost seems like, may I have this, that there is inherent, implicit, the assumption that there is some program that applied to the question gives that specific.
Oh, no.
But this may not.
No, that's
be at all.
not. No, that's not the way it works.
It depends on the language, for example.
No. This one, you could start out with deterministic answers where there's definite. That's why algebra was a particularly easy thing to start with. But ultimately, these are going to be probabilistic. In other words, you want, for instance, you you give it a question, and you give the exact same question in several different answers, see? And or you don't do that. You give it, each question has only one answer and the stuff it's given so far, and yet the best relationship it get could be a probabilistic one.
Let's have some fun. How would you deal with the liar's paradox in this situation? You know, I mean, you have, what I'm trying to say here, you know, the famous barber Seville that doesn't exist, right? He only shaves the men that don't shave themselves.
Yeah.
And so we know that such a object doesn't even exist.
Okay.
And so I mean, that's taking it to the limit of what is, let's say, paradoxical.
Mm-hmm.
I mean, with the in-between, you mentioned, you know, there are some easy things to learn, there are some things that are very hard to learn, there are some things that are no computer, I mean, so the question, sometimes there are no solutions, so I would like to know what your theory may have to say about
Okay, look.
return if it doesn't, it possibly exist, it doesn't exist.
Okay, look, there's a division in the AI community on a certain issue, namely this. In the beginning, most of the people in AI felt that the easiest way to do things would be to work on logical problems that had real answers and get the machine to do reasoning the way people do, quote. And this would be the best approach. On the other hand, there was me and another guy, and we felt that deterministic reasoning and exact logic and so far aren't such a good thing to teach a machine because people rarely use it. And that we were mainly interested in statistical things. So, however, it turns out that some problems to do when you want to devise heuristic devices, or a lot of problems, the best way to do it is to use some logical reasoning. So the question is, how do you do this in a machine that was brought up in a world of probability only, where a probability of 0 never exists? Nothing in this system is given a probability of 0. Nothing is given a probability of 1. If it did, the machine would not be universal. Okay, so how do you deal with this? In logic, you might say that, well, normal logic is sort of an extreme case of probability, and it's only a case where you get these very low probabilities. So you could approach it, but this wouldn't work. There's a tremendous difference in mathematics between a probability of 1 and a probability of anything less than 1. Because a probability 1 means you could extend this thing again and again to infinity, and it'll be okay. If the probability is anything less than 1, it doesn't work. So I was sort of puzzled by this for a long time and didn't know how to deal with it. I finally think I have a way of dealing with it, however. And what you do is this. The machine makes up sort of theories or formalisms. So some of these are mathematical formalisms. The formalisms themselves don't have probabilities in them. The formalism as a whole, as a object, will have a probability, and it'll look for ones that work. Ones that don't work or inconsistent or something like that will get very low probabilities after a while. But it enables a system to do logical calculations. Now, in the case of the barber, I don't know what would happen. I haven't thought about it. I'll think about it. I don't know. It may be that it's difficult to present the problem to the machine. I don't know. But it's a good idea, though. What it does, though, is it's a good thing for me to think about to see whether my model of this, the way it would work, is indeed possible. So for that, it's a good idea.
So the question is, from NKS, we know that there are lots of universal machines, the things which they do easily.
Yeah.
So why not have a space of universal machines and sample through them the same way you sample through models?
Oh, okay. There's I didn't get into this. There's this. Are you talking about the thing of the subjectivity of choice of machine?
No, I'm just saying, in the same way that, obviously, it's universal. There'll be some sequence that will eventually give you some output, right? But it may very well be a long one, or a longer one for this machine, and for that machine. So why not have a space of them? Because they'll have different things which they can get from short strings. They'll have different, coupling.
Okay, you mean using a sort of a set of machines, and you use a weighted average of their predictions, or what?
Well, not weighted average of the predictions. You just have a population of machines. You treat just like models. There's the model, which is this machine sub its input, and you can just ask your overall thing. You just ask, use another machine, use another machine, use another machine.
You mean they're all working in parallel to try to do the code?
You're just nesting them inside the other one. The overall machine just says, which machine shall I use today? I'll use this one, I'll use that one, I'll use that one. And you go through them in the same sequential way, short passes, trying the short strings first with each one, and only then going to the longer string.
I can't say anything.
It just seems to be the same way that you enumerate short models.
Yes.
Or short strings. You can also just as easily enumerate the machines.
Sure.
And use that as a cover.
Sure.
Because each of them is going to wind up being faster at one, so there's quite lots of them rather than just one.
Well, I don't know.
You just slow yourself down. There's too many things to consider. But if you just get some relatively sparse set of them, then you can multiply the number of models you have to consider by very much. And presumably there'll be some problems for which it would be better to have a different machine in your set of models to consider than just the one.
I don't know. The only thing I think of is this seems to be related to a question I was concerned with, and that was the subjectivity of the machines. That is, you choose a particular one, And in a certain sense, you're committed to that one. And this particular machine could be very good at solving certain kinds of problems and not so good on others. So how do you deal with this subjectivity? So I felt that, well, I was bothered by the subjectivity problem for a long time, and I finally thought I had a solution, which was to use all Turing machines and use a weighted sum of their predictions. And then I realized that one, this didn't get me out of trouble at all, and for two reasons. First, that Turing machines aren't the only kind of universal devices by any means. And then second of all, I didn't want to solve the subjectivity problem because it's necessary to choosing a machine is the same as using a summary of your previous experience. That is, using a machine that uses, say, something like Lisp as its primary language means that you are emphasizing the facility in expressing mathematical functions of certain kinds in certain ways. And you wouldn't have designed Lisp in the first place if you didn't have this experience. And in general, every time you choose a machine, what you should do is put into it instructions that make things easy that you think ought to be easy. There's a language called APL, which was designed to be very, very short programs. The programs themselves are fairly inscrutable, but they are short. And this is the sort of thing that you want to do. You want to design instructions for it that make things that you find useful to be easy to program. And this summarizes your experience. So, so getting rid of the subjectivity is something I don't want to do. I want to be aware of it, and I want to have a way to put my experience into the machine. Okay?
That seems to relate to something you were saying earlier, which I was really struck by. Saying how designing the training sequence was the hard part.
Yeah.
The formalism was the easy part. What it sounds, all the things you're talking about are largely focused on issues of formalism and maybe how you're interacting with it. What does it do with the training sequence that seems to feed into the subjectivity matters you're talking about? What are the peculiarities of training sequence design?
Okay, let me tell you. Supposing it's the same as the problem of teaching a child, say, where you have this problem you want them to be able to solve, see, and you don't know why he can't solve it. So you give him other problems and you get some impression of what's wrong, and then say, well, he doesn't know how to do division or something like that. So you do things that emphasize very simple kinds of division or something, but you may have been wrong, see, it may be something else. Now, in this case, you could open up the machine and look inside, but after a while, this isn't very practical. The information is there, but it's not in a form that you could do anything with. It's, the training sequence thing could be as difficult or more difficult than training a human child. It's harder because in the case of a human child, you have many things that in common with them, and here you may not.
Do you feel there are any particular languages that are especially appropriate for doing training sequence stuff, or is it really a subjectivity issue, or depending on what you're trying to train?
It depends on what your training what you want to teach them, and I want to start out with the simplest things I can, and focus on how the learning takes place and things like that. I'm not interested at first in the thing working hard problems at all. Working hard problem is very good for when you have a sponsor to show them you've done something, but if you focus too much on that, I think you could lose sight of something that the sponsor would not be able to understand, which is that the stuff that you've written and the way that they work is something that it will extrapolate well into the future. They may not appreciate this, but I would, and my colleagues might. Okay, well that's pretty much it. At the present time, I'm very optimistic about the future of AI, and I think it's moving in the right direction now, and that it hasn't for the first first 20 or 30 years. And now it's really meeting its stride, and we should have some very intelligent machines in the near future. Okay.